Now I'm going to describe how you can calculate these things called confidence intervals. This example is going to be for the large sample confidence intervals, but there are also small sample confidence intervals that we'll come to later. And the difference between one and the other is just the amount of data that you happen to have. Now, confidence interval is an estimator of an interval which is likely to contain the true population parameter. So if I asked you to estimate what the average weight of an African elephant is, you could give me a range of numbers where you expect it to be. And you'd be pretty sure that it's somewhere between, let's say, 1 ton and 6 tons. You know without any shadow of a doubt that 100% certain that it's between those two figures. And probably you can move the bottom side up and you say it's between 3 and 6. So you've got a narrower confidence interval. But as you narrow it down, you get less sure about whether it's going to be there. So your confidence goes down as you try to narrow it and make it more specific and get more precise in your estimate. So precision is not necessarily accuracy. It just means you're cutting things down and making things much more like a point estimator. Now, what's important for a large sample confidence interval is the normal distribution. So first thing you do is assign a level of confidence, which is usually referred to by statisticians as 1 minus alpha. So 1 minus alpha is going to be something like, say, 95%. So alpha is 5%. So alpha is what's called the type 1 error rate. So that's the probability of seeing a pattern, a difference, or saying that these two samples are different to each other when they aren't. They should actually be the same. So we have a small probability of making a type 1 error. And the type 1 error in this case is that the population mean does not lie in that region. So if I take 100 samples, 5% of the time the population mean will not be in those samples. Now, the confidence interval depends on what's called the critical values of alpha. Smaller alpha gives wider confidence intervals. The higher alpha goes, the narrower your confidence intervals. It also depends on the standard error of the mean, so how much variability there are between the means of different samples. So what you do to get the standard error of the mean is you divide the standard deviation by the square root of n, or you divide the variance by n and then square root it to get the standard error. If you're dealing with small samples, sample size also plays a role, so we'll come back to that later. So remember the normal distribution, so the critical values for having 5% alpha, 5% outside the region you're doing, is minus 1.96 standard deviations and 1.96 standard deviations, because 95% of the normal distribution lies within that curve. So to create the confidence interval for a large sample, and a large sample means more than 30 data points, you use what's called a Z statistic, because it's based on the Z distribution. The critical value is 1.96 standard deviations, or 1.96 standard errors. So the formula for the confidence interval is this. It's the mean of your sample, x bar, plus or minus, because there's two different limits to your confidence interval, one above the mean and one below the mean, 1.96 times the standard error of the mean, which is s divided by the square root of your sample size. For alphas, the critical values change. So if I have an alpha of 0.2, it means that 20% false positive rate, 20% of the time I'm going to get it wrong, I end up with a critical value of 1.28. That means a very, very narrow confidence interval. When I have an alpha value of 0.01, then I end up with a critical value of 2.58 standard deviations, so they're much wider. So a 0.2 level corresponds to the 80% confidence interval, and the 0.01 level corresponds to the 99% confidence interval. So 1 minus alpha. The general formula is confidence interval is the mean plus or minus z critical, whatever the number comes out from this particular table for the alpha you've picked, times the standard error of the mean, which is s divided by square root of n. So let's have a look at the class data. Mean height of women is 1.64, standard deviation of female heights is 0.14, number of women is 100. So from this, let's calculate the 95% confidence interval for female heights. So mean we can put into the formula as 1.64, standard deviation is 0.14, n equals 10, so the square root of n is n equals 100, so the square root of n equals 10. The critical value equals 1.96, so the confidence interval is 1.64 plus or minus 1.96 times 0.14 divided by 10. So the confidence interval is from 1.61 meters to 1.67 meters. That's quite a narrow confidence interval. It's only 3 centimeters above and 3 centimeters below the mean.